continue with your research. So thank you all, everybody, to be here, and thank you to Andrea and Tijani for inviting me. It's really a pleasure coming back to your school after some years, after the COVID and everything. Based on the discussions that we have, I will prepare some slides for you for introducing what I believe is the most important change that we are witnessing in this period on the architecture of mobile networks, and discussing a little bit what are the opportunities, research opportunities we have in this field. So let me start very briefly with some words on my lab, and this is a picture with all people that passed from the lab, including Stefano Paris and other people that were in the lab in the past year. So we have let's say a long tradition of people that now are spread around in the world. And this is the current configuration of the lab with the faculty members and the current PhD students. And the lab covers really, of course, we are many, so we cover many different research topics from wireless networks, which is the topic of today. Then we have a group dealing with soft-defined networks, in particular programmable data planes and network function virtualization. We have a group which is working in the broad area of Internet of Things with different topics within. And also we have some expertise, in particular in the collaboration that we have with network operators on network traffic analysis. So the outline of the talk is in three parts. The first one is the introductory that I was mentioning, and then the second one also for clarifying a little bit the concept of programmability and cloudification. What is important here is really to understand the relation that we have between the use of edge cloud for end users and the use of edge cloud for the network, which is a potential synergy that you can exploit to change a little bit the business model of the operators, and also the way in which you really use infrastructure for not only for transporting bits, but also for supporting the applications and running the programs. Then the last part is on this concept of pushing programmability to the edge, because of course the scarcity of spectrum at lower frequencies is pushing in the direction of increasing the frequencies that we use to millimeter wave frequencies and also beyond. But the problem is that, of course, those kind of radio environments are particularly harsh, and we need to program to, let's say, band propagation in a way which is controllable, and that's why even in that case we can have smart environments that can be controlled and programmed. So let me start with some little list of motivations that sometimes are mixed together, but it's important to focus on the reasons why we are changing the architecture of this network, not just to follow the evolution of technology, but there are a number of specific reasons and forces that are pushing in this direction. One is the introduction of a software-defined approach, even in mobile radio networks, which was apparently not particularly meaningful until very recently, until we realized that controlling in a centralized way this network was possible. And then also opening the interfaces to programmability was an important issue for introducing ways for pushing innovation with more quickly into the network without the closed platform that typically we have in this kind of networks. The other reason is, of course, controlling complexity, which is increasing a lot, in particular with last generation 5G of mobile networks, and controlling and optimizing the network in the usual way is no longer possible because of the complexity that you have in the system, the many parameters, the difficulty in really modeling the behavior of the network, which means that you need to have control systems at different time scales that need to have a global picture of the network and being able to collect information in one place and try to optimize things and control things, which is typically a dream scenario for people that are used to, mathematical models for optimization, everything. If you have everything centralized, it's nice. Distributed things are more complex to manage. Then the other trend is virtualization, which is in addition, right? It's not the main purpose. Virtualization means that you simply want to run the same network nodes on general purpose hardware instead of using specialized hardware. This is of course, not easy. It was already done for a number of other components of the network. But of course, potentially you can make the network more flexible and being able to be updated, which means that the innovation that you can create with programmability can be pushed in the network without changing the hardware. And then interoperability. This is, let's say, also associated to all the, let's say, global technology war that we have in these years. Interoperability means that you don't rely only on one vendor for the entire network, but you can really combine components from different vendors and also even open the network to the programmability of third parties in terms of the software running on it. So for focusing on the architectural chain, I like to describe it with three different components. One is the disaggregation of the network, the other one is the virtualization, and the third one is the cloudification. So let's start with disaggregation. What do we mean with the network disaggregation? This is the typical architecture of a radio access network for a mobile network, where you have what we may say is a problem with the okay. What we call a monolithic base station, where you have the radio unit. It's not really a single device, of course. It's a radio unit connected through typically proprietary interface to the baseband unit, and that's a typical base station, monolithic base station that you have. Then, of course, you have a standard interface to the core network, but you also have a number of proprietary interfaces for the monitoring and logging and control, network management platform, and optimization tools, which is all these kind of closed technology is the reason why you typically have a strong presence of network deployment that are based on a single vendor. The process that was started, what's happening here? Connecting to audio. I don't know if it's audible. I can check if it's audible. Should be. Okay, fine. So what is happening now with 5G is that we are really disaggregating horizontally the network and trying to distribute it geographically in the service area, which means that in principle you can separate what we call the radio unit, connect it to a frontal link to a distributed unit, and then to a central unit, where you typically have only radio transmission here, signal processing, link control in the distributed unit, and all the radio resource management in the central unit. And then, of course, you are connected to the core network that, of course, also depends a lot on the typical deployment that you have on the network. I don't have the time, but this is another interesting direction of change that is affecting a number of different aspects of, for example, managing the different frequency layers. And then, of course, in the distributed unit and the radio unit, you typically maintain the two planes together. It's not only, however, disaggregation. The point is that you disaggregate for a reason, which is controlling the network. And controlling the network means that again, according to the typical software-defined approach, you introduce a run intelligent controller, well, maybe even more than one. Typically, you introduce this near real-time run intelligent controller, RIC, for controlling, in particular, the distributed unit and the central unit. How? Well, again, this is a typical approach based on software-defined working with the controller, with the southbound, which is this E2 interface, which is able to dynamically configure and control the run components and run on top with an northbound interface some applications that are called XApp that can be those that typically we use for radio resource management, for policy enforcement, for billing and everything. In addition, you may have also a non-real-time run intelligent controller, which is more or less the traditional platform for network management. This was introduced with 5G standardization. It's somehow the reference architecture that is now considered, even if not really implemented everywhere in the networks, because again, there are some vendors that are pushing more in the direction of this disaggregated approach, and others that are more trying to continue with the traditional one. And of course, this was also part of a parallel process to standardization, which has been taken by this Open Run Alliance, which now includes really many operators and vendors for standardizing all the interfaces and also somehow making this compatible with the service orchestration and management platform that are typically used in these networks. Again, it's interesting because we are combining the classical approach of standardizing interfaces, vertical interfaces somehow, to an approach which is software-defined, in which you standardize also the APIs and the vertical interfaces to control the different elements of the network. It's weird that they are not combined together. I don't know if in the future we will manage to have a single entity defining all these interfaces and driving the development of this area, but that's the situation at the moment with some vendors that are pushing more in the direction of adopting this Open Run architecture, and others that are more traditional with the monolithic approach. Of course, when we say we disaggregate the network, what do we really mean in terms of the different functions that we have? And this is one of also of the complexity that you have to manage for making different products compatible and really interoperable. For example, in particular between the low part of the stack and the medium part of the stack, defining exactly where you put the boundary, which function you define in the low physical layer and which function you define in the high physical layer is not easy. And at the moment, there are a number of different options that are being considered, which make not all the Open Run solutions compatible with each other. But that's exactly the way in which you separate things, right? So this is a part on the radio unit, this is a part on the distributed unit, and then the control unit uplink, user plane and data plane. Now, when you discuss of Open Run and try to figure out what kind of consequences it can have on the development of the network and the type of innovation from research to the real network that can be integrated, typically this topic is put together with the virtualization process, which is something that of course is connected, but which is ongoing in a somehow parallel plane. And let's try to understand what we mean. So first of all, virtualization is not a novelty for mobile radio network. It started many years ago, even with the standardization of 4G. And as we know, most of the core networks of 4G are basically implemented in a virtualized environment, even if they were not designed for being only in a virtualized environment. And with 5G, we have basically taken the approach of designing a core network which is natively based on the cloud services with a number of interfaces and functionalities that are disaggregated for and can be mapped somehow also to the old functions of the 4G. You also have a very much simplified architecture in the data plane with the G node B directly connected to the this user plane function at the user plane, and all the rest being part of the control plane with different small little functions that are implemented in different components of the core network. And basically all the commercial solutions that you have on the market at the moment, they are based on this approach, and they are, let's say, truly cloud native solutions that can be found. Are we really virtualizing the run? That's one interesting question that we have to ask ourselves, because of course virtualizing the core network was relatively easy somehow. Visualizing the run is a different story, completely different story. In particular, of course, for the control unit, central unit in control plane and user plane, let's say that the functions that we associate to the central unit are relatively similar to the user plane and control plane functions of the core network. In terms also of the time granularity and complexity of the functions that you have. So virtualizing the functions of the central unit is also relatively easy, and there are several solutions from different vendors that are completely similar to the process of virtualization that have been done for the core network. Virtualizing on the other side, virtualizing the radio units, what do we really mean with virtualizing the radio unit, right? It's technology, it's radio technology, right? We don't really have any solution for the virtualization of the radio units. You may say, well, we have software-defined radios, of course, but it's not really virtualization, right? Software-defined radios are mainly used since many years in research for introducing new solutions in the radio part. But of course, it's not something that you can expect to have in a real deployment, even in several years from now. So the radio units will remain a piece of technology which will be on dedicated hardware and very optimized from the hardware point of view for also having a reasonable cost. The discussion and the key point here is mainly on the distributed unit, because having a distributed unit which can be virtualized is the key element in the process of transformation of the network architecture, because in principle you can think of a world in which you have radio units provided by many manufacturers and then controlled by the different providers of the software for distributed units. And in principle, you can even imagine the possibility of changing the software if you change and you want to adopt a new vendor for the software. Basically, the hard work of the radio part is provided and installed once, and then you can continue to change the behavior of the network, producing new things in the distributed unit every time you have something new that you want to deploy. The problem is that you cannot really implement the distributed unit on a general purpose server. You need hardware acceleration, right? So the process of increasing the efficiency and speed of the general purpose processor CPUs is slowing down, as you know, right? And cannot keep the pace of the increase of the data rates of the mobile radio network or networks in general. And this is the reason why, even not only in switching, but also in radio, we are seeing a process in which we have to deal with hardware acceleration. Hardware acceleration is, of course, different from specialized hardware of the past. It's because it's programmable. It is an architecture that can be programmed in a way that you, of course, use a number of functions that are directly implemented in the ASICs, but the way you combine things can be programmed from scratch. I don't have the time for details also on the different types of accelerations that can be implemented, but what is important to know is there are a number of commercial acceleration cards that are now being considered for the hardware acceleration for the radio access network, and there is a big fight between these players for the type of network architecture and hardware architecture that is more suitable for the specific hardware acceleration that you have. So you don't. So then, in a data center for the RAN, you don't put only general purpose hardware. You have to put also some specialized hardware. Otherwise, it's impossible to run the network. And also very well dimensioned, considering the high computing power that is necessary for running the distributed units. Just a little mention of the software-defined radios, which are very important for people like us doing research. Of course, a lot of the innovation that we can test on real test bed for the radio part is based on these kind of devices. Of course, the capabilities of these devices are much more limited than the devices that you have in a real network, but it's very important to test and play with this kind of stuff for testing the solution that you implement, even if then of course before they are mapped and ported in a real network, you need really to have some manufacturer that is interested in implementation or in their project. One other aspect that is interesting of hardware acceleration is also the acceleration that you may have in the data plane. The data plane programmability is something that has been introduced in the data center networking since several years now. But it's important also for the mobile radio networks, because of course, even in this case, accelerating a bit the functions in the data plane of the switches and the servers, in particular the network interface card of the server, is one of the ways in which you offload a bit the workload that you have on the CPU, on some of the functions on dedicated hardware that can be programmed, but can relieve the CPU from heavy load, heavy tasks. In this domain, probably the most important initiative at international level is that of the Open Networking Foundation, that has been managing a number of projects based on hardware programmability. In particular, P4 is the language that is managed by an open source community, which has been used for a number of different projects in this domain. And if you take a look at the open source suite provided by Open Networking Foundation, you will see that in addition to an open source 5G core, an open source CU and DU, you will find also a number of functionalities for what is called the SD fabric, where you can accelerate the functions of the user plane, both in the central unit and in the user plane function. That's interesting because, of course, this is one of the interesting evolution direction that put together the world of switching, typical of data centers, and the world of mobile radio networks. And of course, this part here is fundamental for any cloud initiative now, right? Finally, the cloudification. Okay, we already virtualize things. What do you mean with cloudification, right? The point is that typically, if you really want to take advantage of this kind of architecture, you need to define an infrastructure in the operator networks that is able really to modify the physical infrastructure of the network into something that is basically a set of small data centers, from large data center for the central cloud to very small data center for the far region, where you can host the functions of your network. A cloud platform is not just a set of functions that are virtualized on servers. A cloud platform is something more, because basically it's a system and a platform where you can really deploy the network and the functions in a way which is automated, with operating systems, with hypervisors that can deal with, for example, the scalability of the network based on the computing load that you have. Exactly like in the cloud, right? The cloud is important not only because it's able to host virtualized functions that you can provide in a virtual machine. The cloud is important because it provides you a set of platform for creating the application and running the application directly on the platform. So all the services that are provided in a cloud platform are the key elements that make the cloud so important now for all the internet applications, and important for the programmability. So the software community of developers, they develop the application using the specific functions of Amazon Web Services, of Azure. They learn how to create an application from scratch, because they combine the little blocks that are provided by the platform and put together, right? Of course, we are not still at the point of having an edge cloud that can be combined with a network with that level of efficiency and automation. But that's the only direction that we can expect to have this kind of architecture be successful. Otherwise, of course, if everything must be somehow manually configured, even if you are running your network on a virtualized infrastructure, still the complexity is not reducing, right? And definitely you will not reduce the cost, probably you will increase the cost. So this is a process still ongoing, okay? But it's interesting to understand what does it mean in terms of the changing the infrastructure for an operator, to modify the current architecture into something that is in the direction of an edge cloud, a telco edge cloud, right? We need to distinguish between what we call edge cloud, which may be provided by an OTT, classical OTT in different ways, or what they call the edge cloud for based on even the end user platform, so in end user devices, to the edge cloud for a telco operator, which is something different because it's mainly created for supporting the network and maybe also used for third-party applications. What are the deployment options that we can have of that architecture that I show you in a cloud architecture like this one? Well, there are many. This is not, well, this is the most obvious one, right? Okay, where I have, thousands of cell sites. Then maybe I have a much lower number of far edge sites where I put some micro data centers for the DUs. That for some, in the old naming of the cloud run terminology is what they used to call BBO or hotel. Okay? And then you have regional edge clouds and the central cloud, right? You see some distances here, just to understand that, of course, there is a geographic dimension here that must be considered. For controlling a radio unit, the EU needs to be close, because the maximum delay that you can accept is short. So then the distance cannot be too far. Same stuff for the CU, and then of course for the rest it's easier, right? it's more a problem of reliability and distribution of the functions in different data centers. And then, of course, you have the controller. To be honest, in the commercial Open RAN solutions at the moment, you typically don't have the controller. They just distribute the functions and they try to control the network in the old way. But of course, one of the fundamental elements that we have in this architecture is the possibility to control everything from a controller. And of course, one of the important points is where you put the controller, the central cloud or in the distributed regional edge cloud with all the functions from radio resource management to software organizing network functions to policy control and so on.
That's a good question.
Yes, sure.
So what is the reason for which there's this discrepancy between or this distance between what you call the far edge and the cell site? Can't you have in the principle, I mean, this DU also on the
you can
side? Yeah?
Yes. The point is that if you there are I had to cut the slides, so I have other possible deployment options in which you have a DU together with the RU. Okay, and typically this is, for example, the most the preferred solution from the traditional manufacturers, because of course if you have the DU together with the RU, makes little sense to utilize the DU because you have one DU per RU, while in this case you may have one DU controlling several radio units. Okay. I have an example with some numbers just to give you an idea, right? But for example, in case you have an industrial deployment, I'm not sure I have something here, but let me check. Yes, this one, or maybe this one. This one. This was hidden. For example, if you have a private mobile network for an industrial site, right? Of course, typically you have small base stations. If you have a small base station that are cost effective, probably you don't want to really start splitting things. So you have probably an RU together with the DU. So it's a almost full base station with only the central unit controlling it, right? And then typically you have a far edge, which is a combined cloud platform from the tech operator and the customer, right, for industrial applications. So the same logical architecture can be then deployed in many different ways, depending on the physical infrastructure and the specific application that you have. In this case, the use of a far edge cloud is interesting because it can be partially provided by the telco and partially private cloud by the customer, the user, the industrial user. And of course, because in that case, you have the application and user application running on the same infrastructure, for example. But the same infrastructure of an operator like this one could be, in principle, be used for providing cloud services for external users, for service providers, for OTTs, for example. Okay. The problem is that at the moment, the OTTs are providing their own infrastructure. The operators are struggling to move in this direction, and we don't know what will happen, right? It depends not only on technical aspects, but also on somehow commercial and political aspects, right?
It seems related to that also. I mean, so there are orders of magnitude, so in terms of computing power or storage between this far edge, distributed, and central.
Yeah, there are. Yes. Now we have now a pretty clear vision of all the needs in terms of computing power from DUs and CUs, and typically if you look at the offer by different Open RAN vendors, they have their tables for network dimension. There are several now. Mavenir is one, probably the main one. Samsung, NEC, and now Nokia is moving in this direction. We know it well, right? Traditional, but also new. So now we are having different vendors that are providing their own solution based on this architecture.
What are orders of magnitude of, say, the ratios of these capacities between?
I have a slide. Okay, so again, when it comes to the general architecture, then of course it's important to dimension the capacity, computing capacity, and the connectivity capacity, right? So let's try to see. So this is the traditional one with the monolithic G0 B and the backhauling. Then you may have only the mid-hauling, right? So the capacity for each of these links is in the order of 10 gigabits per second per DU with high capacity fibers. And then the full network has this kind of capacity, right? So you need to have, let's say, up to 510 DUs per IU in a single module. And then, of course, depending on the physical architecture that you have, you can combine multiple modules of this one. What is a DU? The DU is a single dedicated server with nothing else and the hardware acceleration. Okay. If you need more, you basically need multiple servers in a rack controlling multiple groups of RUs. Then, of course, the numbers, it's 6 for, I don't know, Mavenir, I don't know, for Nokia. It depends a lot on the specific technical solution that you have. And definitely, they are not so interoperable like you may wish. Okay. This capacity at the moment should be reduced to 10 gigabit or 20 gigabit, but depends a lot on the number of antennas that you have, for example, right? So if you have a full MIMO here, probably it's more than 20 gigabits per second, depends on how many layers you have, frequency layer you have there, right? So the problem is that it's really transporting here the symbols on from the radio directly on the fiber, right? So if you have too many layers here or too many antenna elements for the massive MIMO, then of course the capacity here will increase. So and the only option is a dark fiber dedicated. We don't have other fancy options like transporting the interface on a network, right? It's a dedicated fiber for that. That's it, right? Then of course, if it comes to the details on the computing power, processors, cores for each specific deployment depends a lot on the vendor, right? So a DU is really a big server with tens of cores and the acceleration cards. Okay. Okay, and just we did also a little exercise with the help of some of the operators to see, okay, this is of course out of the game. You cannot have a far edge on cell sites, okay? But if you look only to the far edge that we call far edge, for a country like Italy, you need to have between 150 and 500, 20, 40 sites for CUs and 4 to 10 sites for the central cloud, right? Then of course ranges, right? Then depends a lot on exactly the facilities that you have and the kind of architecture that you want to implement. But just to give you a rough number of, and probably with France is not much different.
I would suppose, I mean, it all depends on what you run on this. I mean, for what type of applications?
Yes, this is only for the network.
Okay, so then
of course, then to make it worth the effort, then you have to combine it with end user applications to support, and then of course the size of each of these data centers depends on what you need, right?
But I have a question about
yes.
This. I was thinking, so if I have an end user application that needs the edge, as far as I understand, I really need to go at least to the regional telco cloud before having my data, because in the far edge, I still don't have my data plane.
Not really.
Okay.
Not really. This is what I was saying before. For example, in this case, well, this one depends on the configuration of the UI is very important. But in this case, the far edge is typically a combination of the private cloud of the user. It's a private network, yes. If you want to have it in the public network, at the moment, you have to go to the central cloud of the operator.
Yeah.
In the future, hopefully,
cloud, not even on the,
at the moment in the central cloud, they are not. I don't know any operator, at least in Italy, providing this in the far edge. They are all regional. But in principle, in future, the idea is that you can have regions of the operators, not the regions, also only of the OTTs, the cloud providers, that can provide some support. Okay, and how? Apparently, the process is a process in which, for the reason I was explaining on programmability, you will have some partnership between the cloud providers and the operators, just because the cloud provider, they own the platform with all the instruments for programmers. Otherwise, so that's the reason why we see, I don't know, Vodafone with AWS, Orange with Azure, and so on, right? So those kind of partnership, they are not for the infrastructure necessary, but they are for the platforms, right?
And it's nice to start to talk about this because Tijani and I will talk about this kind of. So we will continue the discussion.
Sure.
You will tell us.
I'm a little late, so I just want to show you a little of what we are doing.
Yeah.
So a few minutes just for mentioning you how we believe it's. I mean, that's more research, of course. How we believe we can push this kind of architecture and based on controllers also a little bit to the edge. So of course, radio depends a lot on the specific frequencies that you use, right? We say radio, but we mean really different things. And one of the trends is that of using very high frequencies for the access, right? This was something that was impossible until very recently. Then the radio technology evolved, and now we do have technologies for radio access, mobile radio access at 26 gigahertz, which is the frequency range which has been assigned to 5G. And probably in the near future we will have other spectrum bands that will be assigned to 6G in a similar way. What are the advantages? Of course, that we have large spectrum portions, so that we, in principle, can support extremely high peak rates that are impossible at lower frequencies. But of course, the challenges are the path loss, very high path loss, the very harsh propagation with strong multipath and blockage from any type of obstacle, including glass. Okay. So the idea that we are trying to consider is, I mean, this is something that started more than 10 years ago, right? The discussion on millimeter wave access started more than 10 years ago with the standardization of 5G. And actually with Stefano, we have been involved in one of the first projects on millimeter wave for 5G, right? It looked like something very easy, right? When technology is getting mature, so well, it will be deployed in the network easily, right? The truth is that it has been deployed only for fixed wireless access. Why? Because in that case, the environment, the propagation environment, is controlled and stable. So you control everything with planning. And once you deploy the network, unless you have a new building in between, everything is controlled and not changing. For the case of real mobile access with mobile phones, the story is radically different. We are lagging well behind what was expected. We have very few terminals supporting millimeter wave and very few operators deploying the network at millimeter wave. And one of the reasons is that, in principle, if you want to provide what was promised, you really need to have a very dense network in terms of number of base stations. Okay, not affordable. Period. considering also the economics of the operators in this period, right? So this is the reason why there is now this second wave of research, which is in creating new network components that are for facilitating propagation. This is what we call smart propagation environments or smart radio environments. There are several names for the same thing. What kind of elements can be added to the environment? One is this integrated access and backhauling nodes. Integrated access and backhauling are base stations that are actually simplified base stations that have a backhaul that is based on the same technology of the access, right? They cost less. They can be deployed more easily than full base stations because of the backhauling cost. This is one option. The other option is smart repeaters. Because smart repeaters for a technology like 5G, a repeater is an amplifying forward stuff, physical layer, right? But these are smart because they are based on MIMO. So they have a MIMO antenna for on one side and another MIMO antenna on the other side, which is remotely controlled. So that's the reason why they are called also network controlled repeater. So you have a control plane for controlling the configuration of the antennas of the repeater, okay, which is analog, right? So it's analog beamforming, nothing to do with digital beamforming. Or you can have reflective intelligent surfaces, which are antennas, passive antennas, that just reflect the signal, but reflect the signal like an antenna, right? It's like an array of antennas. So they can be configured in order to change the characteristics of the reflected ray, and configured again by remote. So you have a separate control plane that can be used with a frequency which depends again on how many frequent changes you want to make to the configuration of the network that can change the behavior of a reflected surface. And there are others. For example, you can have smart skins that are static surfaces, which are based on metasurfaces, materials that are maybe kind of the evolution of the mirrors, not just the geometric optics, but something that can be a little bit modified based on the characteristics of the surface that you use. Interesting. Why? Because you can improve a little bit the coverage. You have a shadowed corner, and you can put a reflecting surface for covering that corner, which is not covered. You can improve the quality of a link to a specific area where you have users in order to improve the signal to noise ratio and so on, right? With devices that are in principle, much cheaper than a base station. So instead of densifying the network, you add some new components in the environment to control the propagation. So you can somehow bend the propagation to your needs. It's not just the propagation with multipath that you just observe based on the environment. You control a little bit the propagation environment. That's the idea.
And
yes.
Still being formed, for example?
Yes. With these devices, you can beamform the reflected. So you can have the beam, which is from the base station direct to the RIS, and then the RIS can be configured in different ways. For example, for focusing in a specific point, or even for enlarging the area, depending on the needs.
Oh, yeah.
The problem is estimating the channel, following the user, usual stuff. There are many interesting problems for people like us doing research, right? So from physical layer to system level, right? And much more interesting in the case of the repeater, you can, of course, beamform you get the signal from one side and then you beamform on the other side. But the problem is that you can make the channel estimations only here. So you need to have some pre-configured options for the repeater that must be estimated somehow in the network, in the control plane. So it's not a base station. Otherwise, if we increase too much the complexity, then okay, the cost is the base station. So why don't you put a base station there? Okay. So what we are doing? So we are working in different directions. First of all, we are trying to understand the real contribution that you have from these devices in the general performance of the network. So modeling and optimizing the deployment to understand if they are really useful. And of course, the answer is depends on the cost. If the cost is too high, then okay, makes no sense. Otherwise, there are some specific cases in which they are useful, in particular, some specific devices and others that are not, while in the other cases, they are not useful at all because the cost in the end is comparable or even higher. And then the nice new thing is the dynamic control of the components, extending programmability to them. How? So these are the three areas, right? Modeling, designing and testing advanced control architectures, and creating a large test bed for testing this stuff. So again, the idea is the traditional environment is passive. You cannot control it. You can optimize the network and for providing good service to the end users, but you just have the environment as an input to your optimization, right? In this case, well, it's part of the game. It's part of the problem, right? You can configure it for your purposes. That's the difference. And we did several works in this domain. One is this tool for the optimization of the smart propagation environments for determining the optimal configuration. The goal was not that of really optimizing a real network. The goal was understanding which configuration are suitable with a cost that is reasonable and can make it interesting for deployment, right? So it's an optimization tool, not for optimizing a real network, for understanding the best option and when the network can really benefit from these kind of elements. Then, as I was saying, we are now working on trying to include smart propagation environment into the Open RAN architecture, or as you like to, as you want to call it, with a controller which can be extended to the smart propagation environment, and then testing some applications on top of this. We already have a number of little test bed for this. For example, we have been implemented with a collaboration with Northeastern University in Boston, an architecture where we use Colosseum. So everything is based on open source solutions for integrating the AIB nodes into the Open RAN architecture and controlling the IB nodes, right? And one interesting aspect that we have been working on is in the separation of the control plane and user plane, because the control plane can be, for example, on a lower frequency. So if the IB node is working at 26 gigahertz, the control plane can work on a lower sub 6 gigahertz band, which has, of course, much a nicer propagation and can connect directly the controller to all the nodes. Yes, that's the concept that I was saying. And last one, one of the feedback that we received from discussing with people in this domain is that probably the industrial domain is one of the most interesting application scenario for this kind of stuff, because in that case you can not only control the environment, which can be a very difficult propagation environment for industrial applications. There are some countries that are pushing in the direction of using 26 gigahertz for industrial application. One, for example, is Spain, but I know that France is considering similar things with special mechanism for the licensing. And in that case, of course, the interesting aspect is that you can optimize the network also based on the end user applications. So you have an obvious connection between the needs of the dynamic needs of the end user applications and the network configuration. Okay, that was basically all. Last thing is on on the testbed that we have. So we have a testbed based on the open source solutions. So we are collaborating with Boston for Colosseum, but we also have our own testbed. We are in the process of acquiring new hardware. But in addition, we are also working with companies for an outdoor high frequency campus. So we already have deployed a test bed where we test not only software-defined radios, but also commercial base stations. And at the moment, we have a collaboration between Fastweb, Huawei, Hatonet, and others. And we have this network in the building of our department. And several of the PhD students that I show in the picture playing with this little toy they have. Okay.
So it's open to the members of the lab?
Yes. Now we are in the process also of making it open also to the external community in particular, because we have a big project at national level. So other university wants to come and use the infrastructure. I stop here. I know I was late. Just with the credits to the subgroup of runners is the group of people working on radio access networks. Thanks a lot for your attention. If you.
I had actually just one question.
Yes.
With the introduction of this SPEs, to come back to the story of edge, are we making the edge a little bit further from the end user, or that does not count? It's just controlling program propagation.
I'm not sure I get the question.
I mean, the idea is to make some resources available close to the end user.
Close to the end user, but not really in the devices of the end users.
No,
in the network.
As close as possible, but on the network side.
Yes.
So my feeling from the presentation is that now the closest we can go to the user is at the DU.
Yes.
This is where we can find some resources that can be helpful to some applications.
Yes.
That are maybe delay critical.
Yes.
Yeah.
Now that we are adding some RIS, for instance, these SPEs, are we making the edge a little bit one hop more away from the end user, or it's
not really?
Yes.
Because okay, controlling the environment is through a controller, right? So basically, you extend the platform that you are using for controlling the other components of the radio access network for controlling the environment. The concept of real time in that case is still in the order of hundreds of milliseconds or seconds. It's almost impossible to control the smart propagation environment at a fine time granularity, not because of the distance from the controller, but because of the time it takes for the configuration of these devices and the control interface that you need for controlling them. So if you want to use a low frequency separate control plane for controlling these devices, you don't have a higher data rate. You cannot change the configuration too quickly. You don't have the bandwidth for getting too many measurements from the environment. So cannot be, at the moment at least, really real time, right? Real time in the order of milliseconds, yes, but not the real time at the time granularity of the radio resource scheduler, right? So the timing is not the timing of the resource scheduler, but it's the timing of the network configuration, which is one of the aspects that is interesting. The other problem is who is controlling the environment, and it's the answer is less trivial it may appear. I mean, a network is as an owner. The environment, okay, who is owning the environment, right? Which means that if you have multiple operators in the same area, how they can share the control of the environment, which is probably one of the reasons why this kind of solution for high frequency is not particularly well appreciated by the operators, because they don't understand really who is going to pay for this and who is going to control them. Okay. But it's interesting because again, in that they another interesting direction again in the network architecture is that of having what they are called neutral hosts. So third parties that develop for special environments, they develop the infrastructure and then they host operators, multiple operators using the same infrastructure. In that case, it's more obvious, right? It's a network which is not provided by an operator, it's used by an operator, but controlled by a third entity, which can control also the environment. Think, for example, to big exhibition halls, airports, or this kind of infrastructures. In that case, you need someone else that build the infrastructure, or operators using it, or the underground network, right? That's another example. Yes.
You alluded to, in these smart environments, to a system level understanding of what this brings, right?
Mm-hmm.
So what tools, what machinery do you use to assess that?
We've been using several models. We've been starting from classical optimization tools for modeling the system and understanding with some specific snapshots of traffic types, okay, traffic scenarios. What is the best configuration in terms of, I would say, cost and performance, okay? Deploy and optimizing the deployment. So deciding if and where to put a repeater, a smart skin, you see?
Okay, so this would be the analog of the placement of base
yes,
station,
so,
in a given environment.
Exactly.
Placement of base
we place it, and then we try different scenarios to see when it is convenient, when it is not, and how many do we really install with an optimization tool. Of course, it's not like the classical planning tools that we use, that we expect to use for real networks. It's a way of understanding, because the complexity of the model is really high, right? So if you really try to use simple arguments like the physical layer guys typically do, right? For showing the improvement in performance of one single base station, one single user, and the reflective surface. Okay, fine. We can model everything in the little details and understand with some statistical channel models what is the advantage. The problem is if you bring this at system level, it's much more complicated. And that was one of the ways we have been using for improving it, for understanding something. Then we are also conducting some experiments. So we have now some smart skins that are provided by some colleagues in another university in Italy who are playing a bit for understanding if the expected performance in the test bed are matching the theoretical calculation that we are making. We are now acquiring some risks from some manufacturers, very not prototypes, let's say, not very well performing, but at least we understand the level of configurability that we can have, this kind of stuff. Other questions? Good.
So we can thank the speaker.
Thank you. Andrea.